Hello everyone, good day. So for this video, I will discuss or I will present to you some of the examples showing how to use the formula being discussed in beam design in the previous video. So about shearing stress and bending stress. Okay, so let's get started. So I have here the problem. So 100 mm by 300 mm rectangular beam carries a uniformly distributed load of W. So unknown siya, having the unit of kilonewton per mm over its entire span. The beam is fairly supported at its end if the maximum allowable bending stress is 8.87 MPa and the maximum allowable shearing stress is 0.70 MPa. Determine the span of the beam. So the problem requires you to identify what would be the value of this L. Okay, so let's solve this. Okay, so again, recall that we already reduced the value of the formula for rectangular beam. So for bending stress, we have the 6m over bd squared. Then given by the allowable bending stress, which is 8.27, unknown ang bending moment. Then we have the width 100 and 300 for the depth. But then by simple manipulation, we can find that m is just equal to 12.405 times 10 to the power of 6 Newton mm. But if you observe, or if you will draw the shear and moment diagram for this beam, you can find that the maximum bending moment is WL squared over 8. So if you don't believe, you can solve that so that you can verify if it is true. But anyway, but it's true. It's M equals to WL squared over 8, the maximum bending moment. So zero shear that corresponds to the maximum bending moment. Okay, so using this formula, we will manipulate here so that we can formulate our first equation. So we have m equals to 12.405 here. So for our first equation is WL squared over, equals to 12.405 times 8. So that's our first equation. Now, let's move to our shearing stress. So, shear stress, we reduce the formula into this 3V over 2BD. So, given that the maximum shearing stress is 0.70, then by simple manipulation, we can find that V is just equal to 14 kilonewton. Okay, again, if you draw the shear and moment diagram, you can find that the maximum shearing stress is WL over 2. You can test your understanding about shear and moment diagram so that you can verify if it is true. Okay, so using this formula, by substitution, we can formulate again another equation, which is WL equals to 28 kilonewton. That's our equation 2. Then we have two equations. We will divide equation 1 by equation 2 here so that we can find that L is 3.54 meters. So if you have that cross section, 100 by 300, so the required length is 3.5. Another example. So we'll read the problem. A wooden rectangular beam is subjected to various loading as shown. Draw the shear and moment diagram and label completely. Design the beam using nominal dimension. So we need to design now the beam. So given this configuration, so we have this beam, then this transverse load, we have this reaction 1, reaction 2. We need to formulate the proper size of the beam with respect to this transverse load. Okay, so first thing we need to do is to calculate the reaction 1 and reaction 2 in order for us to draw the shear and moment diagram. Okay, so let's start with summation of moment in R2 equals to 0. So first component is this R1 having a perpendicular distance of 1, 2, 3, 4, 5, 6. 6 times 1.2, so we have 7.2. Then next one is this couple, 4.5. Its vertical distance or perpendicular distance of the two couple is 0.9 plus 0.9. So you wrote 0.9 multiplied by 2, so 4.5. Then another one is this 18 kilonewton. This 18 kilonewton perpendicular distance here is 1, 2, 3. 3, 1.2. So we have 3.6. Okay, next, this 22 kilonewton. So 22 kilonewton negative, since it's the opposite direction of our assumed direction for the positive. So its perpendicular distance is 0.6. Then next one is this 18. So perpendicular distance is 2.4 here, 1.2 plus 1.2. Okay, for this incline, you have two components. So you have x and y. So for y, you have 22 sine theta. So theta is unknown. Then perpendicular distance going to R2 is 1.2. Then for x, you have this. So negative 22 cosine theta multiplied by 0.30. So here, class, this is the perpendicular distance of x component going to R1. So we just need to calculate the value for this sine theta and cosine theta. So recall your trigonometry. So we can formulate this. That sine is just equal to opposite over the hypotenuse. Then for cosine is adjacent over the hypotenuse. Okay, then by simple manipulation, you can find that R1 is just equal to 17.14 kilonewton. Okay, so we have the value for R1. Then let's move and finding the value for R2. So the same process, but another technique so that you can find R2 is through the use of summation of force along Y. But this time, we will be using summation of force along R1, moment on R1. So the same process, we can find that R2 is equal to 18.06 kilonewton. Then using this value, we can formulate the shear moment diagram. So why it is important to draw this shear moment diagram? So using shear moment diagram, you can find this value, the maximum shear and the maximum bending moment. Okay, sir, why is that the maximum value is negative? So negative maximum value for is just a sign. So the maximum is 18 because here is 17.14. So it's just a sign, class. Then for maximum moment, bending moment, it's 32.77 kilonewton. Okay, so using this, we need to design. So we need to design using formula for rectangular beam. So again, recall, the maximum bending moment is 6m over bd squared. Then by simple manipulation, you can find this equation that bd squared is just equal to this value. Okay, since we're designing, again, recall in your structural loads that we need to specify the size of our structural elements. This time, we will assume. So let's say that we will try, what if the depth or the width of our beam is 200? So what is corresponding depth? So by substitution, you can find that D is just equal to 281. Okay, the 281, we will not use that 281 because in real scenario, when we go to shop or let's say store, when you buy structural elements that having a size of 200 by 281, di juga kapalitan na, okay? So let's say that 300. So to check, let's use the shear formula, the shear stress formula. So by simple manipulation, you can find that the shear stress using that size, the 200 by 300, you will have a shearing stress of 0.45 MPa, but the allowable is 0.70. So it's safe. So you can use 200 mm by 300 mm as long as that the shearing stress will not exceed to this load. Like I recall in a structural load that the load must be less than or equal to resistance. So it's one of the possible size dimension for your structural element. So you can use 100. Let's say you use here 100. Okay, so let's say 100, then you will have the corresponding D. Then if you check if it is safe, then you can use also that. Okay, so it depends. It's designing class. So as long as that you will satisfy this equation, that it is safe. If it is safe, then it is good design. Okay, so I think that's all, and see you in our next video.